So, have you ever stopped to wonder how scientists keep track of the millions upon millions of chemical compounds out there? How does a chemist in Tokyo and another one in Toronto talk about the exact same molecule without getting their wires crossed? Well, they do it with a special code. It's a universal language for building matter, and today we're going to crack that code.
All right, take a look at this. Now, to most of us, this looks like a password that your computer randomly generated for you, right? A jumble of letters, numbers, and hyphens. But to a chemist, this isn't just a name, it's a complete blueprint.
I know what you're thinking. It seems impossibly complex, just total gibberish. But what if I told you there's a really simple logical system behind it all? A system so elegant that once you get the rules, all that complexity just kind of melts away. And what you're left with is a crystal clear set of instructions. And that is exactly what we are going to do. In just the next few minutes, we're going to crack this code together. I promise, you'll be able to look at a name like that and see not just a bunch of letters, but a complete picture of a molecule.
So where do we start? Well, we start with the absolute foundation. Just like any language has an alphabet, the language of chemistry is built on a backbone of carbon. Understanding that is the very first step to becoming fluent.
Okay, so the very first rule is to find what's called the parent chain. Just think of it like the spine of the molecule. All you have to do is find the longest possible path of connected carbon atoms, and boom, that gives you the molecule's last name.
And that last name comes from a core vocabulary. Seriously, think of these as the first 4 words you just need to know. 1 carbon is methane. 2 carbons, that's ethane. 3 is propane, and 4 is butane. Pretty much everything else we're going to talk about is built from these roots.
But of course, molecules aren't always nice, simple, straight lines. Come on, that would be too easy. They have branches, these little side chains that stick off the main backbone. So, how in the world do we account for those?
Well, these branches are called substituents. So a 1-carbon branch is a methyl group. A 2-carbon branch is an ethyl group, and you can probably see the pattern. We're just adding a few more words to our vocabulary here. And this leads to a really crucial question. If you have a 6-carbon chain with a branch, how do you specify which of the 6 carbons it's actually attached to? You can't just say methylhexane. That could mean a bunch of different things. It's just not specific enough.
The answer is so simple, it's brilliant. You just number the carbons in the parent chain. And here's the key rule. You always start counting from the end that gets you to the very first branch with the lowest possible number. This one little rule just eliminates all the confusion. So, let's look at the name 2-methylbutane. We can actually decode it now. Butane tells us it's a 4-carbon chain. Methyl tells us there's a 1-carbon branch. And that 2 tells us that branch is hanging out on the 2nd carbon. See, it's literally a set of instructions.
Okay, so we're good with a single branch. But what happens when things start to get a little more crowded? Let's take a look at how the system handles molecules that have multiple branches.
The system just scales right up. It's the same logic. You find the longest chain, you number it to give the branches the lowest possible numbers, you identify every single branch, and hey, if you have 2 of the same kind, like 2 methyl groups, you just say dimethyl. 3 would be trimethyl. You just put it all together in a logical order.
Now here is the crucial point. When you have different kinds of branches, you list them alphabetically. And here's the tricky part that gets everybody. You alphabetize based on the branch name itself, so ethyl or methyl, and you completely ignore those prefixes like di or tri.
And this brings us right back to our original puzzle. The correct name is 3-ethyl-2-methylhexane. So why is that? It's simple. Ethyl starts with an E, and methyl starts with an M. E comes before M in the alphabet, so ethyl gets listed first in the name, even though its location number 3 is higher than 2. Now, just when you think you've got it all figured out, chemistry throws a curveball. What happens when the carbons in our chain are connected by double or even triple bonds? Well, the rules change, but just a little. A double or triple bond is now the most important feature of that molecule. It gets top billing. So our numbering rule gets an update. You now number the chain to give the bond, not the branch, the bond the lowest possible number. The bond always takes priority. And we also change the ending of the parent name. For a double bond, our "an" suffix becomes "ene". For a triple bond, it becomes "ine". So ethane can become ethene, and propane can become propine. Simple as that.
Take a look at this 3-carbon chain with a double bond. Prop for 3 carbons, ene for the double bond. But where is it? We number the chain to give that bond the lowest number, so it starts on carbon 1. The name is prop-1-ene. See? Every single part has a specific meaning.
So now we have all the pieces. Let's just step back for a second and look at the big picture. Because this isn't just about memorizing a bunch of rules. It's about appreciating the power of a perfectly logical system that was designed for absolute clarity.
You know, this simple change in the name's ending is incredibly powerful. Just by looking at the last three letters, ane, ene, or wine, a chemist instantly knows the fundamental bond structure of the entire molecule. It's a perfect example of just how efficient this language really is.
This system, which is officially called IUPAC nomenclature, is what ensures that any chemist anywhere on the planet can draw the exact same structure from a single name, with absolutely zero ambiguity. It really is a triumph of logic and collaboration. As the source material puts it, the goal is to provide unique, systematic names. And you know what? It succeeds beautifully. It turns what could be total chaos into perfect, predictable order.
And that kind of leaves us with a final thought to chew on. We've just seen how a problem that seems overwhelmingly chaotic was solved with a clear, logical language. It really makes you wonder, if we can create a perfect language for millions of molecules, what other complex parts of our world are just waiting out there for the right system to make them simple?